Oh. So what I'm going to do today, we're going to talk about related rates. And this was the lecture I gave earlier this week. For some reason, the recording didn't work. I'm not sure why, but we'll do it this week. We'll do it right now. So this is section 310, related rates. And number one, well, they give 6 tips, things that can help. And sometimes these are necessary, maybe they're not, but these are things that can help you understand the problem. And working with a problem on paper is really important. It can actually be very hard to keep all these ideas in your head, and things can be crossed and confused. So these are 6 tips that can help you out. So first off, draw a picture. Pictures can help you understand exactly what's going on, and then they kind of give your brain a little bit of a break, because now with that picture sitting on the page, you can use all your energy now to, well, do other things with that picture. For example, locate and name constants on your picture, say like the length of a rectangle or the angle in a triangle. And then also you can name variables. These are things that you might need to solve for along the way to solve the problem, or it could be something that we're looking for to begin with. Also, they call this step 2, but you can use this picture to highlight additional relationships, like say the relationship between an angle and say certain walls or a base of a triangular region. Now, something to keep in mind when we're working with these, I mentioned, for example, we name variables, and sometimes we're naming variables that we might need to solve along the way to solving our problem, but we want to always keep in mind what we're looking for. And this is going to help us come up with some of these additional relationships. So we want to keep in mind what we're looking for. So ultimately, when we're dealing with these additional relationships, maybe these are inspired by what is it exactly we're looking for. We're going to try to come up with equations, ways of describing these relationships. And what these equations will do hopefully they're going to relate or connect the variables. And our constants. Now, with these types of problems, these related rate problems, these are going to involve derivatives with respect to time. So a very common thing is we'll come up with an equation and it has variables in it. And we're used to these variables being sort of, I guess one way of putting it is standalone. For example, if you say take a look at the area of the circle, A area equals pi r squared. And so we just treat r as a number we put a number into. We replace r with some number. And what we're going to do is different. We're going to start looking at these variables as being dependent upon time. So that means r is really a function of time, r of t. And because now the area, pi r of t squared, well, contains a function of t, that means the entire area, A, is now A of t, now a function of t. So what this will give us the opportunity to do we're talking about rate, we're talking about change. We're going to come up with these changes. We're going to find them in our equation by taking the derivative with respect to time. And that's going to give us rates or derivatives of these functions with respect to time in our equations. And then finally, what we're going to do, we're probably going to solve for rates, is what we're going to usually do. Not always, but we're going to solve for rates. It means we're solving for a derivative, like the dA dt, or the change of area with respect to time. And we're going to do some substitutions. We'll have an idea of what the rate of change for the radius is, dr dt. We'll be given some number for that. And we'll replace dr dt with that number. And once we make our substitutions and do our arithmetic, we'll have a value for dA dt, will give us the rate of change of the area at a particular time, and the radius has a particular rate that we're given. So we're going to use known values of variables slash other rates to compute the unknown rate. So let's do an example. So let's say we have this, our pi r squared, or the area of the circle. So let's write an equation relating dA dt and dr dt. So the way we're going to do this, we look at this, we just see A and R. How the heck is T getting in here? So what we're going to do is this. We'll assume R is a function of T. That's how we have to do this. This is sort of one of these things you just got to do in this section. So that means A is now also going to become a function of T. So because R is now a function of T, now A is a function of T. So we want dA dt and dr dt. Well, these are functions of T. We can take the derivative of these. Now, what we're getting to here, now pi is a constant still. It's always going to be a constant. Pi is not going to change with time. It's always 3.14159 and so on and so on. This is a chain rule situation because we have a function, r of t, inside a squaring function. So we're really looking at this. So we have an outer squaring function and an inner function, r of t. So when we do the chain rule, we're going to differentiate the outer function first and leave the inner function on the inside. That's the first thing. And then we multiply that result by the derivative of that inner function. There's pi. The derivative, like the derivative of, say, x squared, is just 2x. Except this time, instead of having x, we have r of t, that inner function. Next, with the chain rule, we multiply by the derivative of that inner function. And in this case, it'll be dr dt. So, simplifying things a bit, we get dA dt is 2 pi r of t, that's this right here, just putting the pi in between, dr dt. And that's our answer. Here's an equation relating dA dt to dr dt. All right. So let's say we have this. So let's say we're given that dx dt is -2. And we're also given, or we're asked to find dy dt when x is 3 and y is -4. So again, this is going to be kind of a new thing. It takes a little bit of time to get the hang of it. But we're assuming that there are rates, dx dt and dy dt, that we can discover. So for that to happen, we need to make x and y not just variables, they need to become functions. So again, we're going to make that assumption. X is really x of t, and y is y of t. So what we really have is x of t squared plus y of t squared equals 25, or x of t squared plus y of t squared is equal to 25. So again, we got this outer square function, inner x function, outer square function, inner y function. Now we need to get a dx dt, dy dt. And so the way we can do that, take the derivative of both sides. So we're going to get this. Now, here the derivative of a sum will be the sum of the derivatives. And then the derivative of a constant, well, that's the change in a constant. Constants don't change. The change is 0. No, derivative of a constant is 0. So now we got that chain rule again. So we take the derivative of the, say, like the x squared function, leaving the inside here, and then we multiply that by the derivative of this x function. So 2x of t times dx dt plus 2y of t times dy dt is equal to 0. So when we think about what this question asked in the beginning and what it gave us, it said dx dt was -2, and we're going to look for dy dt when x is 3 and y is -4. So here's dx dt. That's supposed to be -2. And for x of t and y of t, well, when they say x is 3, they mean a time. We're assuming we're at some time where x of t is going to be 3, and y of t at the same time is going to be -4. And dx dt is going to be -2. So we have the pieces here, and we just solve for y of t. So it says x is 3. So that's same way as saying the function x of t at some particular time. X will be 3. Dx dt is -2. And y is -4. Or we get -12 minus 8 dy dt is equal to 0. So we're going to add this to this side. -12 is going to be +8 dy dt. Divide both sides by 8. -12 over 8 dy dt. Divide top and bottom by 4. -3 over 2 dy dt. And that is going to be our answer. Cool. Well, that's right. This is recording, so the habit I'll ask for questions. And if any questions about these, just send me a message. Let me know. Let's see here. So here's one that's kind of complicated. And a lot of the information, including the equation we're going to be working with, is provided to us in the problem. But it goes like this. So there's water, there's a spherical bowl, and water is flowing out, like it's flowing out the bottom of the bowl. And it's 6 cubic meters per minute. The volume of water in the bowl of radius r is given by, here's the equation, and it's kind of not a trivial equation at all. Oh, I squared. And you're probably wondering what y is. Okay, volume, okay, v. R, that's our radius. So what's this y doing here? Well, for y's coming in, say we have, say the center of our bowl down towards the bottom. This is our radius r. What y is, let me see, I think I'm missing, double check. So there's our y. And they also give us another value, a lowercase r. Let me just check here where this r play a role. Yeah, yes. So r is going to be for another part of this problem. We'll deal with r later, with lowercase r. But y is basically the water line, the water level, and tells you how deep the little pool here is in this bowl. And well, that's going to be our y showing up here. So let's suppose capital R is 13 meters. So now we come up with our first question. What is the rate, the water level, y is changing? Well, let's see. When the water level is 8 meters deep. What is the rate the water level y is changing when the water level is 8 meters deep? Now, this could be a little confusing. The rate the water level is changing, water level is 8 meters deep. Seems like we've got two different things going on here at the water level. Well, in a way we do. And there actually could be very different things. When we talk about the water level being 8 meters deep, that means when it's at 8 meters, whatever moment of time we're talking about is going to be at 8 meters. Now, it's not fixed at 8 meters. This is a subtle part. As time is passing, this volume of water is leaking out at 6 cubic meters per minute. So it's always changing. So when it hits that 8 meter depth, it's just hitting it for like a nanosecond, and it's going to keep on going. So for an instant of time, it's going to be 8 meters, and then it's just going to drop. Now, so that's one fact. There's going to be a point where this thing is going to be 10 meters, 9, 8, 7, and so on. We're interested at that moment of time, that flash of time when it's at 8 meters. Now, this other reference to the water level is its rate, how fast it's actually dropping. So that's change with respect to time. This first reference, this tiny moment of time that we just visit and we just pass on through, or this depth that we pass on through. And then this other reference to water level is a rate, or the change of this with respect to time, or dy dt. Another thing that could be kind of intimidating about this equation, so we actually have two different things we're dealing with. A value of y when it's 8 meters, and then a rate dy dt. The other thing that's kind of intimidating about this is this v. What do we do with v? When do we know anything about the volume of this thing? How much water is actually in it? Well, what we can do is this. We're going to ultimately, we need a dy dt in here because we're talking about a rate of the water level. So we're going to need a derivative dy dt. That means we need to take the derivative of both sides. We're going to get dv dt. So what that does, it kind of gives us some breathing room. We've been told what the volume is, or the rate of change in the volume. I'm sorry, the rate of change, not the actual volume. But we've been given what the rate of change of the volume is. 6 cubic meters per minute. So we do know what this derivative is, dv dt, automatically. It's been given to us. So following the advice of the beginning of this section, we're going to take the derivative of both sides. But again, we're going to make this assumption that the water level y is always changing with time. It's a function of t. And so we'll take our v is pi over 3 y squared 3r minus y. This is now going to be a y of t. Squeeze in a y of t in here. And we can take the derivative of both sides. dv dt is d dt. There's our constant. I'll rewrite this as an inside function with an outside function. And we have a 3r minus y of t. So this is going to give us dv dt is pi over 3 times, and we're going to get not only a chain rule situation, but we're going to get a product rule situation. So this could be our f of t, and this could be our g of t. So you have a product of f of t and g of t. So that means product rule. So still have our pi over 3 on the outside here. So we'll have d dt y of t squared times our g of t plus our y of t squared times d dt of 3r minus y of t. We're going to get that. So here we're going to get that chain rule. So again, derivative of x squared is 2x. This time we'll have 2 times whatever's on the inside times the derivative of what's on the inside. And then we have multiplied by this. Then we're going to add to that this just on its own times the derivative of this. Well, the derivative, this is a difference, so the derivative of the difference is the difference of the derivatives. Derivative of a constant, remember r is going to be 13, it's going to be 0, and then this will be the dy dt. So what we're going to get, 2 y of t dy dt times 3 times r, and again that's going to be 13. That's a constant. Plus y of t squared times, and then the derivative constant 3r, because again that's going to be the number 13, so this whole thing is going to be a constant, minus dy dt. So what's going to happen here, 0 minus dy dt, that's just negative dy dt. So negative dy dt times a positive y of t squared, well, positive times negative is a negative y of t squared dy dt. So positive y t squared, negative dy dt, negative yt squared times dy dt. So now we make those changes. We're told we want to find dy dt when, remember, this is equal to dv dt. We want to find dy dt when the water level, y of t, is equal to 8. So this is what we have. We're told the radius of this tank is always 13. The radius of this bowl is 13. That's not going to change with time. This is a constant. So, and we want y, which is we've now assumed to be y of t because it's always changing. We want the change dy dt at the instant this is equal to 8 meters. And we've also been told that dv dt, well, that's going to be 6. So let's take a look at this. So here's our equation. Well, I have a lot to work with. Well, this is 6. That's going to be 8. That's 8. 13, 8. And so the only thing that we don't have a number for is this here and that there. So what we're going to get, dv dt, which is 6, is equal to pi over 3 times 2 times, well, this is 8, and then times dy dt, we don't have that, times 3 times 13, R is going to be 13, minus the instant 8, water level at this instant, water level is 8, minus 8 squared times dy dt, and then that's going to be it. So 6 pi over 3, this is 16 dy dt, 39 minus 8 minus 64 dy dt. (31) minus 64 dy dt. And let's see, 16 times 31. $496. Minus 64 dy dt. Okay, it's simplifying down. All right. So divide both sides by 432 pi over 3, or multiply both sides by 3 over 432 pi. We'll get here. Oh, and I made a mistake here. I'm sorry. So this is -6. I need to make a point here. This is -6. dv dt is going to be -6. And the reason is that the negative here, it symbolizes that the volume is shrinking. So this is a negative rate of change because the volume's always getting smaller. So if you had, say, the volume and you have a rate of change, if it's a positive rate of change, it's increasing the volume, so the volume builds. But if the volume is dropping, that means the rate of change is going to be negative. And so that means dv dt is actually -6. -6. All right, and so this will reduce down to -1 over 24 pi is dy dt. All right. So again, any questions about that, let me know. So let's do a part B on this one. So what about this is the little r. What is the radius of the water, r, little r, when the depth is y meters deep? So this one, we're going to take the picture they've given us. We're going to do a little bit of analysis to figure this out. So again, let's draw a picture here. Let's bring this back. Y, R, and then let's say the radius, let's give this the radius R is 13. So what we want to do, we want to find this. Now, a little clever trick here. We've got a triangle. So this triangle, we know the hypotenuse. We're looking for this side. Is there something we can do about this? Can we call this something? And we actually can. So this is the center of the bowl. I should mention that. And again, one way you can tell this is the center, and this is not drawn to scale, unfortunately, or drawn to correct proportions, but the radius, and this would be the same radius, I apologize, this is 13 meters, and this is 13 meters. So because this thing has a radius of 13 meters, the distance from the center to any of the sides is going to be 13 meters, despite artistic license on my part. Sorry. So this is 13 meters, and this is also 13 meters, though it doesn't look like it. It's supposed to be. It's supposed to do something that's more like this. Anyway, we got this other version. So what this means is this. If this is 13 meters, just like this is, despite what the picture says, well, then this distance here is 13 minus 1. So if this was, say, 8, like last time, well, if this is 8 meters, and the whole thing is 13, well, then this little piece here would be 13 minus the 8. That would give us, say, 5, this example. But whatever y is, subtract it from 13 to get this piece here. So what we end up getting is this. This triangle that's the triangle we're going to work with. So what we want to do is we want to relate when a relationship between R and Y. So what we can do is this, the Pythagorean theorem. This side squared plus this side squared is equal to the hypotenuse squared. Or, and we won't expand this. We'll keep it a little bit packaged up. We're going to solve for R. And then we can square root both sides. We'll get R is the square root 169 minus 13 minus y squared. And that's it. That's the relationship we're looking for. Now you might be asking, how come we don't do plus or minus here? The reason is that since R is a distance or a measurement, or a dimension, I should say, it's going to always be positive. We're not going to have negative length, is what we're trying to avoid. All right. So there we go. There's we could expand this. I guess they do that. If we do expand it, follow through. So if we FOIL this, we'll get 169 minus 26y plus y squared. These will cancel. But if we'll go through and put all the terms in here. You're distributing your minus sign. And again, those go away. And there you go, a more simplified version. All right. So that little clever trick, knowing despite my drawing, that any line going from the center to the edge of that bowl is always going to be a measure of 13 meters. And you can use that little trick where you've got your radius, you know it's 13, this part's y, this part's 13 minus y. And then you can use your Pythagorean theorem to come up with that equation. So let's take a look at part C. So let's say this. So what rate is R changing? When the water level is 8 meters deep. So once again, we're going to ask this question: what's going on in this picture at the water level of 8 meters? And in that case, there's some instant time when this reaches 8 meters. So again, I'm going to assume y is a function of t, or I'll use an equal sign. And this is going to cause r to also become a function of t, because now it contains a y of t. Squaring y of t, so we'll do that. And what we're going to do is take the derivative. There's a dr dt. Well, that's what we're looking for, the rate that r is changing. The d dt, yes. So taking the derivative of this, it's going to be 1 over, it's actually 1 over 2 square root 26y of t minus y of t squared times the derivative, and this is the chain rule, I'll go over this in a second, of 26 y of t minus y of t squared. So just a reminder, let's say we're taking d dt of the square root of f of t. So what this is, it's d dt of f of t to the 1/2, or it's going to be 1/2 times f of t to the 1/2 minus 1. So it'll be 1/2 minus 1. And then by the chain rule, we multiply by the inner function, df dt. So we get 1/2 f of t negative 1/2 times df dt, or one half times 1 over f of t through 1/2 df dt. And again, that's just the square root. So we get 1 over 2, that's our 1/2 here, square root f of t df dt. So what's happening here? F of t in this case is what's on the inside of the square root. So 1 over 2 square root f of t, 1 over 2 square root, and then what's on the inside, that's our f of t, times the derivative of f of t. So that's where this is coming from. It's a little complicated in this one, a lot of pieces, but oh well, such is calculus. So you have 1 over 2 square root 26 y of t minus y of t squared times, and so we'll distribute the square root, d dt 26y of t minus d dt y of t squared. So looking at these derivatives, constant will pass through, and we have the derivative of y of t. This is the chain rule. So what we'll get (26) dy dt minus that square function on the outside, and then derivative of the inside function. And so that's what we're going to get. So we've got our dr dt. So what can we do? Well, we want the water level at the depth of 8 meters. So what y is y of t is equal to 8 meters. So we can put something here. Why do we do dy dt? Well, to be honest, this is where we go back to part A. So that in some of these problems, they'll have you hop around. We actually know what dy dt is, the change of the water level, when the water level is passing by 8 meters. And that is dy dt is negative 1 over 24/5. Highlight. There. So we actually have all the pieces we need. dr dt is equal to this once we make these substitutions. And again, it's going to be negative. Just like with the volume, since the volume is dropping, that means its rate of change is negative because the change is causing the volume to disappear. it's reducing it. It's sort of like you have a bank account, and if your bank account's getting smaller, that means money is going out of that account. It's a negative change in your money. This is negative also because that water level is dropping. It's not gaining. It's not positive increase. It's negative. You have a negative change or a decrease. So plugging things in, we have 26. Y of t is 8 minus 8 squared times 26. dy dt is -1 over 24 pi minus 2 times 8 times -1 over 24 pi. So 26 times 8, 208, minus 64. This will be -26 over 24 pi. Negative and negative will be positive, so you have positive, and then 2 times 8 is 16 over 24 pi. Remember, this is what dr dt is equal to. This is 144. Oh, lucky. Square root of something that's going to be like, well, it's going to be 12. Times -26 plus 16, -10, 24 pi. So simplifying down, and we'll multiply, we'll get, well, I'll just take a big leap here. Well, we can do this. -10 over, let's see here. And that's going to be our answer. And again, it's negative, because you think about this bowl, as the water level drops, well, the change in volume is negative. The change in the depth is negative. They're both shrinking. But also, as you head to the bottom of this sphere, you notice the distance going across it? It's always getting smaller. So this little r is bigger than this one, which is bigger than this one, which is big. It's eventually going to become 0. So even this little r is getting smaller and smaller. So we're going to see negative change as well. All right. So let's say we have this. So let's say you're videotaping a car race where your camera is 132 feet let's see, from the track. Now let's say the car, maybe this is sort of a victory lap. There's only one car on the track, so like a victory lap. The car is going 180 miles per hour or 264 feet per second. How fast is the camera angle changing when the car is in front of you? So you're videotaping this car race and your camera is 132 feet from the track. There's a car on there, again, for some reason, there's just this one car. Maybe all the other cars are way ahead, or this car is way behind, or this car is way ahead, one or the other. This car is going 180 miles per hour or 264 feet per second. How fast is your camera angle changing when the car is in front of you? So what it means is this: you're watching this car go by, you know, this sort of horizontal stretch on the track. And you're sitting here and you're watching the car and you're watching the car and you're watching the car, and your camera, it's changing angle as it follows the car. So when the car is right in front of you, what that's going to mean is that right when it's this 132 feet, this part of the track where the distance between you and the track is smallest, that's that 132 feet. So that's what we're meaning by the car being in front of you. And you draw a picture of what's going on. This might help. So here's your racetrack. And the picture they actually give you in the text give you something like this. This is the distance, 132 feet. And let's say you have your car doing this. So here's your camera. Your camera angle is that angle theta. So this is the part, this is a problem where the tips of drawing have to come up. Well, this one they do give us, thankfully, but we want to understand what we mean by in front is the car being right here. So because this is in feet, we'll probably want to go with a speed that's also in feet. So let's go with a speed of 264 feet per second. Now, in this picture, there's something else we can label. The distance from the car and this location in front. I'm going to call this S. So what we want to do, why would we do anything with the S? Well, the speed of 264 feet per second, that's a change of distance over time. Or you can think of it like this. It's going to be delta S over delta T. A change in this distance over the change in time. Or if we want to say it really, ds dt. So a little slick, I'll admit. that this distance is changing as this car moves. So it's going to have a ds dt. Now, how is it changing? Well, if the car is going at 264 feet per second, that tells us how quickly this distance is changing. And is this distance s getting smaller or is it getting bigger? Well, if we're starting on this side, s is getting smaller. So the car, for it to be in front of us, is going to approach from this other side like this. That means s is shrinking. That means its rate of change is going to be negative. So again, that idea that we've got this quantity shrinking means the rate of change is negative. So we can handle s. We can come up with a ds dt, and we can give that ds dt a number. But how do we relate these things? Okay, so if we need to take the derivative of s, we've got a number for that. But how do we relate them? Well, what we have is a triangle. There's a theta, an s, and a 132. And we're going to take the derivative of our variables. So theta was going to become a theta of t, d theta dt. So what's going to happen is relating these. So this is an opposite of theta. This is adjacent to theta. So we could use tangent of theta is opposite over adjacent. Or tangent theta of t equals s of t over 132. So now what we can do, take the derivative of both sides. Now this, again, we're going to use chain rule. So we get a secant squared theta of t times d theta dt. That's the change in the camera angle we're looking for. And this will be 1 over 32 times ds dt. And we've got a number for ds dt, negative 264. There is kind of an issue. What's theta of t? Well, there's a clue in this. The clue is going to be this. We want to change d theta dt of our camera angle when the car gets here. Now, if you notice theta, as time passes, if the car does this angle is going to get smaller and smaller. And when the car's right in front, the angle is going to be 0. So in front, that tells us theta of t is 0. So now we can plug everything in. Secant squared of 0 times d theta dt is 1 over 32 times negative 264. Now, secant of 0 is 1. Because remember, secant is 1 over cosine squared of theta. And cosine of 0 is going to be 1. Square that, you still have 1. 1 divided by 1 is 1. 1 times d theta dt. This negative 264 over 132 This is just -2, and so d theta dt is -2. This is going to be radians per second. So that's how fast the camera, and then the reason it's negative is, again, you think about, this is the in front, we're watching this car, the angle between the camera and this vertical is shrinking to 0. And so since it's shrinking, the rate of change is going to be negative. All right. So let's do something a little different. So in part B, what is d theta dt a half second later? So take a look at what's going on here. There's our car. So we're watching this car. It's 132. And the car's headed in this direction. So what happened is we found d theta dt when the car's right in front of us. We found d theta dt when the car gets here. So now we're asking, how fast is our angle changing a half second after this? So say when the car gets over here. So how do we figure this out? Well, once again, we'll call this distance s, and it's going to be changing as s of t. Now, here's the thing, though. Now the car has passed this point in front. And as the car keeps going, s of t is getting bigger now. So the rate of change is now positive. And so that means ds dt is positive 264 feet per second in this situation. Because now s of t, measured from here to here or to here or to here, or to, s of t is just getting bigger and bigger. So that means a positive rate of change. Now, we want to answer a question. We have a half second later. We can actually answer this. What is s of, well, I want to say 1/2. I guess we could say 1/2, but what is s of t at, well, I guess I could have just used s of 1/2. So if we start our timer over again, we say this is time 0. Well, how do we find, could we find S of t for t equals 1/2? It turns out we can. We know that this car is going 264 feet per second. So if we take 264 and multiply by 1/2 second, seconds cancel, what we'll get is 132 feet. Another thing you could say is that because this S of t, because the speed of this car is constant, we could also say that S of t is the velocity times time. You could do that as well. Come up with a little function like this. But if our car is traveling 264 feet per second for 1/2 second, how far has this car traveled? Well, 1/2 times 264 is 132. If this car was traveling for 1 second at 264 feet per 1 second, well, then the car's traveled 264 feet. So anyway, that's the way we can figure out what this is when t equals 1/2. So what this does, we now have a triangle. So 132, 132. We have our camera. We still have our equation. We have our tangent. This is our theta here. Theta is going to be S of t over this, the distance from the track. Here, a little differently. So over S of t over 132, or what we found was that secant squared theta of t d theta dt is going to be 1 over 132 times ds dt. So what can we do here? Well, we got ds dt. We know what that is. It's now positive 264. Now, we want to look for d theta dt. We're missing theta of t. Now, in this case, we can figure it out. Theta here is, we have two sides of a triangle. We have an opposite of theta and an adjacent of theta. So to find theta, we can use the tangent of theta is 132 over 132, or equal to 1. So what angle is a tangent that gives you 1? Well, theta is pi over 4. So we have to do a little extra work with this one. So we have our equation. We figured what this is. You know this is now positive. We had to figure this out. In other words, if this car is traveling 264 feet per second for 1/2 second, then the distance it's traveled is 132 feet. But our equation requires us to find theta. Well, we know this. This is the distance from the track. So what angle has an opposite of 132 and adjacent of 132? Or put another way, what angle has an opposite equal to its adjacent? Well, that's an angle of pi over 4. So now we can replace that theta of t. And let's see, secant is 1 over cosine squared of pi over 4 d theta dt. And again, this is now going to be a positive 2. And cosine of pi over 4 is rad 2 over 2. So we'll get 1 over rad 2 over 2 squared, because we have cosine squared, d theta dt. Or 1 over 2 over 4 d theta dt. And this will come out to 2, or 1 over 1/2, which reduces 1 divided by 1/2 will be 2. And then we get d theta dt is 1 radian per second. And the reason it's going to be positive, we think about this, your camera's here, you have 0 degrees. Your camera's watching the car go by. This angle is always getting bigger. So that means there's a positive increase, positive rate of change. So that's really it for section 310. It's a lot of stuff in here. Definitely, these are problems that take practice. If you have any questions working on these, let me know. I'll be checking my email throughout the break, and be more than happy to go over some of these. So other than that, have a wonderful day and have a wonderful break.